Okay, we'll go through a little bit of this together to help you out. This first line, just some notes on this paper that I sent home. You can tell if things are inverses by doing G composed with F and F composed with G. And if both of those yield X, then those functions were inverses of each other. We'll practice that a little bit here in a little bit. Please make note that the little -1 key on your calculator does not mean inverse, it's reciprocal. So please make note here that F inverse of X is not meaning the reciprocal of X. It is, or reciprocal of the function. It is the inverse, which we'll get to figuring here in a little bit. What they point out here in example 1 is that simply the inverse of a set of ordered pairs is to switch the x and the y of the ordered pairs. So 3, 2 is 2, 3. 4, -6 is -6, 4, and so on. Okay. In order to find the inverse of a function, you first want to write the function as a y instead of an f of x. So y equals 3x plus 10. And then, of course, switch x and y so that x equals 3y plus 10, and do whatever is necessary to get y back to being solved for. So the rest of that is kind of self-explanatory. And that's what these examples just kind of to show you how to find inverses, and we'll get to that here in a little bit. Okay, so we're supposed to tell if these are inverses. Now, one way to do that would be just simply taking one of these functions and finding the inverse, and hopefully it matches up with the other one. But we can tell if they're inverses a couple of different ways. This way they want us to do it as f composed with g, and then we'll also have to do g composed with f. So f composed with g says take the g function, place it inside the f function, and do some simplifying and see what happens. So as I simplify this, I would distribute the 2 and get x minus 4 plus 4. Minus 4 plus 4 cancels out, so I just get x. That's a good sign that these are inverses, but we can't stop yet. We've got to go and do the reverse of that as well, and that would be g composed with f, which would simply be f put into g. So it would be 1/2, parentheses, 2x plus 4, parentheses, minus 2. Distribute the 1/2, we would get x plus 2 minus 2. And the plus 2 minus 2 cancel, and we're left with x. So clearly these are inverses of each other because we got x when we did f composed with g and g composed with f. Okay, let's look at a couple that are not inverses. So if we do f composed with g, that would mean g is put into f. And we would find out that distribute, you get x plus 6 plus 6. Well, x plus 12 is definitely not just x. So this proves that these are not inverses. Okay, so we're going to also show you another way to show whether things are inverses or not. And that would be with the calculator to graph them. So let's go to y equals, and let's graph the h on number 3, which they said is x squared minus 2. And let's graph the g, which they said was the square root of x plus 2. And let's graph that a third thing called just x. And by graphing this with respect to x, what we're looking for is symmetry along the line y equals x. So let's graph this. Okay, this is kind of confusing. It doesn't really look like it's going to fold over the line y equals x and have symmetry. But also, I'm a little bit confused by one thing here. We can't use the entire domain of negative infinity to infinity on x squared minus 2. And here's why. I'm just going to graph the square root of x plus 2, which we know looks like this guy that's been moved left 2. So what is the range of that? The range of that is from 0 to infinity. Well, since inverses just switch x and y's, just flip-flop them, the range would be what the domain of its inverse has to be. Let me say that again. The range of this graph would be the domain of the inverse graph. So let's go look at y1 now, and let's make it have a restricted domain that is 0 to infinity. So insert parentheses around this whole thing, and then say we only want x to be greater than or equal to 0. That would be the range of this one, would be the domain of this one. And if I do that, when I graph this, it kind of cleans it up a little bit. We see that, and then let's check it with the line y equals x going through the middle, and we see, yeah, I do believe this is symmetry on both sides of that line. Now, a little bit of concern, we've said, was that the calculator screen is rectangular, and rectangular screen means it's longer than it is tall. And therefore, you're going to see just a slight distortion here in this piece that goes to the right versus the piece that goes up. That slight distortion should not convince us that these are not inverses, though. Okay? Okay, so number 5 just says find the inverse, and we're given a bunch of ordered pair. So the inverse of f would be the set of numbers whose ordered pair gets switched. So the 1, 3 becomes 3, 1. Negative 5, 2, negative 5 becomes negative 5, 2. And one more, the 3, 6 becomes 6, 3. There's the inverse for 5. Okay, I'm going to find the inverse of 16. The 3-step process is first, change f of x to y. The second is switch x and y. And the third is to undo PEMDAS until you have y by itself. So I think we would need to square both sides to get into the inner part of that square root. And then we would add 4 to find out that the inverse is y equals x squared plus 4. However, remember the range of the original is the domain of its inverse. So the range of the square root of x minus 4, the range would be 0 to infinity. So the domain of this one is 0 to infinity. Okay, so I went to the next page here, and we're going to look at number 5. It's a little bit different. The 3 steps are the same. First, write it as y equals x minus 2 over x. Secondly, switch x and y. Now it gets a little bit interesting. We are going to multiply both sides by y, which, if I clean that up a little bit, y times x equals y minus 2. Solving for y is not that easy because there's 2 places where there's y's involved. So the way you solve anytime you have multiple y's involved in the problem is gather all of the y's to one particular side. So I'm going to just simply subtract y to gather all of the y's to the left side of equals. Now that all the y's have been gathered, each term over here has a y in it. And because each term has a y in it, I could factor out a y. And because I've now factored out a y, I could divide out the x minus 1, which would leave the y by itself. So y equals negative 2 over x minus 1 is the inverse. And you could prove that to yourself by graphing it and checking for symmetry on y equals x.